That is porting Hadoop over to the HPC world. I think you may have heard we announced earlier this week that we in fact are now releasing a product on this basis. But I just wanted to try and provide more of a technical background of what exactly is going on. So the motivation for doing this really was that we've been talking a lot with people around the community, especially in the HPC world, the enterprise world, and there's a certain amount of resistance to Hadoop from the standpoint that Hadoop comes with its own ecosystem, its own resource managers, its own launch system, etc. And it kind of meant that you had to take a look and say, well, I have to learn a whole new file system, I have to learn a whole new resource manager. I can't share resources in the sense that I cannot stand up a Hadoop cluster and run something else on it. It only runs Hadoop. And Hadoop won't run on my HPC clusters, and so I can't take use of them. Then we took a look and looked at the scaling rate. Even though Hadoop can be arbitrarily large number of nodes. Sorry, Yarn and the Hadoop ecosystem doesn't support NPI or PGAS or SHMEM or any of the other techniques one's used to using in an HPC environment, and so you can't use machine learning libraries like Scale-a-Pack, for example. And you see a lot of effort going on in the Hadoop community, where people are spending a lot of time and effort rewriting what already exists in some of these other libraries that they could have accessed, but the ecosystem doesn't support. So we wanted to try and address that, and the way we chose to do it was to say, let's port Hadoop over to the ecosystem, the HPC ecosystem. And there were three basic elements you have to address: the resource manager, file system, and then access to the advanced programming languages. So for the resource manager, we partnered, as was mentioned earlier, with our friends here at Adaptive Computing because they've got a really good one called Moab that runs on top of Torch. Okay? It's a very mature platform. A lot of people use it. It's got good fault tolerance. It's got great schedulers. And it's got a very nice scalable launch system, and it has all the wire-up support for the high-level programming languages like MPI. So we said, okay, let's take the Yarn part out of the equation of Hadoop. We're going to port over and use Moab instead. Then we said, well, the file system, let's go ahead and replace that with Lustre. And we'll use the enterprise edition of Lustre from Intel, from Lamb Cloud. Because that's really good and mature. It's got good fault recovery, and it's got very high performance. So we'll use that as the file system. And then for advanced programming models, what we're going to do is we're going to support these three: NPI, SHMEM, and PGAS. And what we'll do is we'll provide Java interfaces to it, because Hadoop's a Java environment. These languages typically don't have Java interfaces to them, so we'll add the Java interfaces. And then the other thing we're going to have to do is that these guys all assume that all the processes get launched at the same time and are running together. But in Hadoop, that's not true. Mappers and reducers run at different times. You might have some mappers running, but not all of your mappers running at any given time. Same thing's true of your reducer. Not all of your reducers are running at the same time. So if you want to use these languages, you have to change them and enable asynchronous operation. So we extended MPI to be able to run in an asynchronous mode where some of the processes are alive and some are not necessarily alive at any given time. But they still want to be able to communicate with each other when the other guy comes to life. So the way this works, in a typical Hadoop application, you have a client that's going to actually run. Basically that's what the user types the command. The client launches an application master, which actually executes the application. And this is done this way in Hadoop because people like to be able to shut off their notebook computer where they started the whole job and walk away, but have the job continue to run. This is a little different from HPC land where you don't do things like that. But you still want to be able to do that and provide a Hadoop person with a typical Hadoop environment. So the client gets a single slot, launches the application master, and tells it, this is what I want to run. The application master breaks that up into map and reduce steps. And it forms a queue. It says, okay, I'm going to run 100 mappers, I'm going to run 30 reducers, and here's the data each of them is going to look at. So the next stage is the application master comes back to the resource manager and says, I need to run, or would like to run, 100 mappers. Yeah, the resource manager, MOAB, takes a look and says, well, I don't have 100 resources I can give you right now, but I can give you 30. Okay? So the application master then says, all right, I'll take 30. That's okay. And what I'll do is I launch what I call worker bees. My developer calls task runners. Basically, what these guys are, they're the ones who are going to actually execute the map and reduce steps. These guys come alive and they call back to the application master and they say, I'm ready. And the application master assigns them a data set and the map or reduce function, whichever one they're going to execute. And these guys then go ahead and execute that stage. When they're done, they call back and tell the application master I'm done, and they go ahead and get the next assignment until the job is complete. Now, notice I didn't say anything in here about data locality. Right? So normally in Hadoop, you would try and put the mapper somewhere next to a disk, on a node where there's a disk that has the data. And we didn't do that here. And we didn't do that because we're running on top of Lustre. Okay? So there is no data locality anymore. I'm running on a parallel file system. All data appears to be local to me. So what we did is we extended the Hadoop file system to basically provide a hook to Lustre that simply comes back and says, when you ask me where a file is, the answer is it sits right where you are. Just go ahead and read it. What that does for us, it does two things. One, it means that the data is pulled across the network, which you might think might be a problem, but actually in our tests so far, when you're looking at a high-performance network like InfiniBand, for example, or something like that underneath, we have yet to be able to max out that pipeline. But the other thing it does is it eliminates the shuffle. Now in Hadoop, what happens is every time I run a mapper, it reads the data, does its filter, and then it writes the data, the results out on the local disk. Then when the reducer starts, it has to go and ask somebody to send him whatever data belongs to him from that disk to wherever the reducer is. That shuffle operation is quite often the most expensive part of the Hadoop operation. There's a lot of I/O and a lot of data movement being done. That shuffle operation is completely eliminated here. I may have confused it here. How do I think I confused it if I touch the screen. Yeah. I confused it. My apologies. I confused it. There we go. Yeah. Thank you. So some of the optimizations you look at doing with you to the future a bit. Well, one thing is that in Hadoop, if the data set, say coming out of a mapper, if the data that you're analyzing is too large for physical memory to hold, what you do is you wind up spilling that data, the excess data, onto your local file system. It's called spill. In this case, you don't have a local disk in order to run the typical HPC operation. You have diskless nodes. So you're spilling across the network into the Lustre file system. That works. But that can start to overload the network a bit if you're doing it a lot. So if you have an application where you're doing that, you're seeing that a lot, the simple solution is you add some NVRAM or SSD onto the nodes where that's happening, and the problem goes away. There's some cost associated with it, so we don't require it. It actually runs pretty well, just spilling across the network where it needs to. But if you run enough jobs, or you're spilling enough data, it can begin to become a bottleneck, and there's your solution to throw that in. The other thing that you can do, now that you have network file systems underneath, is you can consider putting an abstraction layer in here. Remember what I said earlier, that the way we tied into Lustre is we actually changed or extended the Hadoop file system and put in a Lustre file system integration. Okay, well, if you replace that Lustre file system integration with an abstraction layer like PLFS, for example, okay, now you have a single sort of set of code in here, but the PLFS abstraction layer can drive multiple file systems in parallel. So I could, in fact, have a Hadoop file system sitting down here that's absorbing streaming data, which it does very well, pulling that in. I can have my application read out of that file system without having to know that it's actually reading from the Hadoop file system. It doesn't care where it's getting it from. Analyze the data and write the structured data out onto my Lustre file system, okay? Which then gets sucked up by an MPI application and executed and analyzed. It's some kind of machine intelligence algorithm, for example. All of that can be done transparently where this application doesn't have to have any idea what the source of the data is. I could even, if I wanted to, add a data management layer down here. And say, for example, I'm upgrading from HDFS1 to HDFS2. Well, I don't want it to stop all my applications to upgrade the data, move it across, and restart everything. So if I'm using an abstraction layer, I can be, all I say is, I want to read this data. Well, some of it's in HDFS1 and some of it's in HDFS2. But I don't care, okay? Because the abstraction layer is hiding all that from me. So the benefits we've been seeing from this is, first off, of course, we get the shared resource utilization. We've got some test customers who are running this now, and they're able to run this on a Moab cluster that's running an HPC job. As far as that cluster is concerned, the Hadoop job is just another job. There are no Hadoop daemons anywhere in this system. There's no Hadoop file system daemons, no Hadoop yarn daemons, nothing in there. So it's just another job, running like any other job. It launches about 1,000 times faster than Hadoop does. So if you've got a Java application that's got a lot of map-reduce phases in it, like some people do, so I've seen applications that have hundreds of map-reduce phases that they execute. Every one of those is launching 1,000 times faster than it would have under yarn. So it makes a big compression in the execution time. Like I said earlier, there's no shuffle operation. So again, you get some time back. So where's the trade-off? You're trading off and you're pulling data across the network, and so therefore you are slowing down a little bit on the data pull time, but you're gaining it everywhere else. And so the overall execution time on the applications we've tested has been anywhere from 17 to 30% faster if we ran it under Hadoop. You get enterprise quality systems. You're not running on something that's relatively immature or young. A lot of it's already been around in your institution already, so you're not having to retrain your IT staff, you don't have to retrain all your users. They're running on very similar systems they're used to. They're very familiar to them, and therefore you get a certain benefit to the cost of operation right off the bat because you don't have multiple types of systems running around, and you're able to take advantage of what you already have. So that's the proposition of what we did. A little bit of technical background, as I think the guy said in the announcement. We're looking for beta people that want to test this. Work with us on this for a general release next year, first quarter next year. And that's what we have. Questions, anybody? Yes, sir. The question was, what do you do about fault tolerance under Lustre? And the answer is Lustre already has a fault tolerance mechanism built into it. And so we just rely on the Lustre fault tolerance system. Well, metadata's backed up in Lustre as well. It's supported. Right? Yeah, metadata in Lustre is given the exact same RAID, if you will, backup that the user data does. So it's still high availability, high availability. Yeah, I know. Luster's been pretty hardened for that. It's mostly InfiniBand that we've been using, but it'll run just fine on 10 GB as well. 1 GB would not be very good. The 10 gig E or infinite band. Yeah, these are the ones. I don't know. I am not. I don't know if these guys have or not. I know one group we've been working with has a luster installation, for example, that they've had tied to their HPC system, right? So they just sort of took another tap off of it and added this capability in a new cluster they had using the same file system, which there is, if you, the question was, how do I find out, how do I register or inquire about the beta program? If you go over to the Intel booth, they will give you a little handout, I guess it is really, that's got the email address on it that you can contact us through that, and then we'll be happy to talk to you about it.
Very much more than United presentation.
Good. Good. That'd be great. That'd be great. We'd love to see it. Talk to you about it. Any other questions? All right. Well, thank you very much. I'll be around and.